So now, Tarzan. Question is, why does the vine break? So let's see if we can apply this analysis to thinking about Tarzan. So here's Tarzan hanging from a vine. And for simplicity, let's say Tarzan's a big guy, so his mass is 100 kilograms. All muscle, absolutely. And so the gravitational force downward on Tarzan is what? So 980 newtons, which means the force exerted by the vine, if his momentum isn't changing, he's just hanging here. Force exerted by the vine, 980, not 9, has got to be, we'll call it F sub t is 980 newtons. And here I'm writing magnitudes, not. Okay, now let's think about Tarzan swinging. We know that in our story the vine breaks when he gets down to the bottom of his swing. And as long as the vine, even if the vine stretches some as he's swinging, it's nearly a circular arc. And of course, when he's at the bottom of his swing, there's a kissing circle. So let's say that he started here and he's swinging down to here. And so here's the vine. Here's Tarzan. Here's his momentum. And we want to know what the force the vine is exerting at this moment to turn Tarzan's moment, to hold Tarzan up and turn his momentum is. And so we've actually got the same scenario, don't we? Because we need to figure out the direction of DPDT, and then we figure out the direction of the net force, and we picked conveniently a point in his swing where this is very easy to do. Okay, it's a little more complex here, but it's actually worked out in the book. You can do it. So here's what we're going to do. We're going to do exactly what we just did. We're going to find a value for DPDT. That tells us what the net force has to be. We know the gravitational force, so we can figure out the force by the vine. So let's figure out a few pieces of this qualitatively first, and then we'll actually. So let's work out directions and some relative magnitudes first, and then we'll do the math. The arithmetic, rather. So here's question 1. Tarzan swinging from a vine. At the bottom of his swing, what's the direction of the rate of change of his momentum? Okay. So remember the procedure. It's not necessarily something you can eyeball. Now, something we can't prove yet, but you probably sort of guess it, is that the magnitude of Tarzan's speed when he's here and when he's here at the same height is actually going to be the same. We're going to need energy to actually really make that clear, but so his momentum here and his momentum in equal time on the other side have the same magnitude. Yep. So it's straight up, isn't it? And notice that there is kind of an easier way to think about this now, because we saw that DPDT always pointed, that the perpendicular component of DPDT always pointed toward the center of the kissing circle. Okay, so this is DPDT, but it's also DPDT perpendicular. Okay, that's good. So we know the direction of DPDT. What's the next question we're going to ask? What is, we don't need to do that, what is the direction of the net force on Tarzan at the same instant? Okay? So we know DPDT's up. What's the direction of the net force on Tarzan at this instant? Yep. So the net force is in the direction of DPDT, isn't it? It's a vector. Okay, so we've got the net force up. We'll make that. Okay. So now we're working on both sides of this equation. The net force. Okay, so now we want to find, but the net force is due to more than one thing, isn't it? So what are the objects in the surroundings, if Tarzan's our system, what are the objects in the surroundings that are exerting forces on Tarzan that we need to worry about? It's not the case of the moon and the earth where the only force on the moon was, non-trivial force on the moon was due to the earth. So what are the objects in the surroundings exerting forces on Tarzan? Okay, so if you said for, you didn't read the question very carefully. Is centrifugal force an object? No. No. Remember, our procedure, forces have to be due to objects. So we've got objects. We've got the earth. So this is the earth. We've got the vine. And the rule is if you can't name an object in the surroundings, then there's not an interaction. There's not a force. So centrifugal force isn't an object. It's a word that you may have started to associate with motion in a circle. But it's not real. There's no force. There's no net outward force. Now, in fact, the force due to the earth is so let's draw a force diagram for Tarzan. Here's Tarzan. We have the gravitational force due to the earth. We have a tension force due to the vine. Well, this actually is out from the center, so you could describe it as centrifugal, but it's not the object is the earth, so the force we're going to count is the earth, okay? Now, okay, you said that the net force on Tarzan at this moment is up. And there's only two objects in the surroundings that are exerting forces on Tarzan, the vine and the earth. So what do you conclude about the relative magnitudes of these forces? Okay, which arrow should be longer in my diagram, or should they be the same length? No, the vine hasn't broken. Vine hasn't broken. He's swinging. Well, that's interesting. Okay, so we better talk about it. If we've got two forces, this is actually really important. So you actually should, even if you're not going to pay any attention to anything else, you should pay attention to this one, including people in the front row. We can wait until you're finished with your computer here, okay? All right, if you're going to do that, you need to sit in back. If we have a force down and a force up, and that's it, and what do we say the direction of the net force was? And net force up. Okay, if these two things are equal, what's the net force? 0. So it can't be up, can it? So which force has to be bigger? The vine. So it better look that way, hadn't it? Questions about this? So you have to take your conclusions seriously. If the net force is up, there's no other way that can happen, is there? Okay. Fine. Calculate it. Or do you want to do it together? You want to do it together? Let's do it together. Okay, we'll do it together. All right. So we have this is important enough that we're just going to take time to do this. Okay, so that's the rate of change of his momentum. And this is going to be equal to F vine sub y plus F gravitational y. Right? So we've got the y component of so we have 100 kilograms times 13 meters per second squared. At the moment, the length of the vine is 5 meters. And that's going to be equal to the force of the vine. Yes, exactly. At the moment, the length of the vine is indeed the radius of the kissing circle. And so we have the force due to the vine plus the gravitational force, which we worked out to be 980 newtons in the minus y direction. So who's got a calculator? 100 times 13 squared. So this side comes out to 3380 newtons is equal to the force due to the vine minus 980 newtons, which is the gravitational force. So what's the force due to the vine? It's that plus that, which is 4360 newtons. So this poor vine has to exert a force of 4360 newtons when he's swinging, when it only had to exert a force of 980 newtons when he was hanging there. So it has to do a lot more. Think about those interatomic bonds stretching. Yeah. That's pretty strong.